So at this point, we're going to look at the optimized short circuit resilience of the windings. So as Tom mentioned, one of the major aspects for the insulation material is for mechanical stability of the windings. And specifically, the role is to support these windings during short circuit events. So in the image on the left, if we look at typical transformer forces in core type transformers, the inner winding of that transformer will want to, during a short circuit event, pull itself kind of in on itself, both radially and axially, while the outside winding will want to kind of push itself apart in both directions. So one way to ensure that the windings are sufficiently supported, specifically axially in this case, is by selecting the correct material for the radial spacers. And by doing so, you select something with the optimal compressibility characteristics. Again, as Tom said, the compression or compressibility of this material is critical for short circuit resilience. So compressibility can be affected by multiple properties. However, most significant is the surface condition of that material. So when we look at compressibility of radial spacer materials, we consider material that has a milled surface pattern or an original unmilled surface with the screen pattern intact. So the images on the right show two variations of material. On the left is unmilled or unsurface condition modified material, and we can see in that bottom left photo the screen pattern that is applied or is created during the manufacturing process. So this screen pattern during the process helps to compress the material and the drainage and dry the material properly during the pressing. On the right, or during the manufacturing process for radial spacers, that screen pattern is removed to allow for a much more consistent thickness, and also more importantly, the compression characteristics that we are desiring. So you still can see the kind of remnants of that screen pattern on the right. However, it is actually almost wholly, completely removed during this manufacturing process. So when we look at these materials in the lab, we did some laboratory testing of various spacers and showed a number of different things looking at compressibility. So just for reference, this testing was all completed per the IEC standard. So we're using a bedding pressure, an initial pressure of the spacer stack of 1 MPa, and then compressing that stack up to a pressure of 20 MPa, and really measuring the difference between those two. So the compressibility on the left-hand graph, we have the three spacer thicknesses, 1.5, 2, and 3 millimeter, all with the milled surface condition, so where that screen pattern had been removed. And on the right-hand side, we are looking at the unmilled spacers where that screen pattern is fully intact following, as it was following the manufacturing process. And focusing first on the right-hand side with the screen pattern intact, the unmilled version, we can see a big difference or a big impact based on the thickness of the spacer. So 1.5 millimeter has significantly more compressibility, or compresses much more than when we have, say, a 3 millimeter spacer. And that is really because the screen pattern on each spacer is approximately 1/4 of a millimeter. So the impact on that when you have a 1.5 millimeter spacer is much more than a 3. Also, just to note here is that the IEC specification requires a maximum compressibility of 1.5 millimeter spacers, or 1.5 millimeter material, of 10%. So you can see we're well within the IEC limits, being 10% for 1.5 and then 7.5% on the 2 and 3 millimeter. So we're well exceeding those, but there is this big difference based on the thickness of the material. However, when we look at the milled surface spacers, we have very consistent results and is really independent of the thickness of the material. So this compressibility is really measuring how much does that material compress under a known pressure. And then looking back on the right-hand side, where we look at reversible compressibility, this is measuring really how much of that compressibility comes back when you remove that pressure. So in the testing process, going from 1 MPa up to 20 and then back down to 1, in an ideal case, you would see 100% reversible compressibility. All of what was pressed out returned when that pressure was removed. Similarly to what we saw in compressibility, the unmilled surface, you see a significant difference based on thickness. With the thicker the material, the more reversible that compression. Again, really dictated by the screen pattern ratio between the screen pattern and the total material thickness. The IEC limits here for the 1.5 is a minimum of 45% of that compressibility has to be reversible, and for 2 and 3 millimeter is 50%. So again, well exceeding those IEC limits, but variable based on thickness. Whereas on the milled surface materials, first we see higher reversible compressibility, meaning more of that thickness that was compressed out actually returned, and much more consistent with between different thickness of spacers. So the next thing we're going to look at is the optimized stress distribution by understanding material permittivity. And here first we look at relative permittivity, otherwise known as dielectric constant, relates the effect of the material on the capacitance of an object compared to air. So when we talk about relative permittivity, it is all kind of relative to air, which is 1. Transformer oil is around 2.2, while theoretically pure cellulose is 6. We say theoretically because it actually cannot be measured, the dielectric constant of a pure cellulose material. It will always have some sort of air encased in the material that will be measured as well. So when we look at typical transformer materials, we have listed here a few different options. The low density material is high val. Shown here is an approximate density of 0.95 with a relative permittivity of 3.8, while the high density material T4, higher density with 1.2 and also a higher relative permittivity of 4.6. Shown on the far right hand side of this table is the oil absorption. And really what we see is the relative permittivity of the material is dictated by the density, which allows for more or less oil to be absorbed in that material. So for high val, for example, we see a much higher oil absorption, which we have more transformer oil within that or inside of that material, bringing the relative permittivity down compared to that of T4, which absorbs less oil. So when we look at how the relative permittivity of the solid material dictates stress, we first need to understand that dielectric stress distributes inversely proportional to the relative permittivity. Showing here the calculation method for understanding that, and I don't want to go really into a lot of detail in that, but really just understanding that the stress distributes inversely proportional. On the right-hand side of this slide, just want to show an example of two different systems, one with high-density pressboard and mineral oil, and the other being low density. If we refer back to the previous table, we see high density press board relative permittivity of 4.6 compared to low density material of 3.8. All other conditions being the same applied voltage, transformer oil still at 2.2, and the dimensions of those materials being the same, we can see that the electrical stress within that system has shifted. The press board in the high density material is 1.3 versus 1.5 in low density material, and the dielectric stress in the oil has shifted when you're using high density material of 2.7 to low density material, a stress of 2.5. So in this example, by exchanging high density material with low density, and ultimately bringing the relative permittivity of that solid closer to that of the liquid, that stress is shifted, and the stress in the liquid was reduced by 8%. And typically, when you look at transformer designs, the fluid is really what will set, or the stress in the liquid is what will set the design clearance. So the ability to reduce that stress helps in that regard. So looking at an example, if we have, again, replacing the high-low barriers between two windings from high-density press board T4, exchanging that with low-density press board of high val, resulting in the shift of the stress, you ultimately see an increase in the percent margin during the insulation dielectric analysis, or IDA. Shown here on the left, looking at a field line in the high-low space under the uniform field, so not really looking at the effect of the static rings or on the end of the windings, but looking in a uniform field area. With T4, in this case, there was a negative 1% margin, and simply exchanging that T4 material with high val, the margin was increased to a 2%.